So here's a quick overview of relativistic motion. One of the postulates of relativity is that we can't exceed the speed of light. So we need some ways to handle situations where you would have added and subtracted velocities and considered how they worked in a Newtonian fashion that don't exactly work for relativity. And you think about the classic problem where you're riding in a car and you throw something forward. So now the speed of the object that you just threw has the speed of the car plus the speed that you gave it when you threw it. Well, when you have the problem where you're in a spaceship and the spaceship shoots a light ahead of it, if that spaceship is moving close to the speed of light, then the light is moving at the speed of light, you can't add those two anymore. And so we have a set of equations to handle that include kind of a fudge factor for relativity. And you can see those equations right there. And so U is the summed velocity, the velocity that the observer would see the laser light going at, in the case of the spaceship and the laser light. And then U prime is the actual speed of the light, and v is the velocity of the moving object. So one of the things with light moving at light speed is it experiences Doppler effect just like sound waves do. So you've got a source that's emitting the light and it's moving. So how do we handle the idea that it can't speed up past the speed of light? And what happens with light is that you get a shift in the wavelength. So as the light source is moving away from the observer, the light waves are stretched, so you get a redshift. And if it's moving towards the observer, the light waves are compressed, and so you get the blue shift. There's equations to handle the frequency and wavelength, where the subscript S is the source, and in this case, OBS is the observer. So v is going to be the speed of whatever the source of the light is. Motion includes momentum, and so when we're talking about masses moving, we're going to be talking about momentum. And conservation of momentum doesn't hold with relativistic speeds if we just use the classic formula, momentum is mass times velocity. So you have to have a relativistic correction. And this really is a practical piece because a lot of the experimental work done with particle accelerators relies on those type of equations where you have the relativistic momentum. And just like other motion at low velocities, the relativistic momentum is very much the same as classical momentum, but once you get closer to the speed of light, you're going to end up with a big difference. And it actually approaches infinity as the object's speed approaches the speed of light. Once again, things that move have kinetic energy, and so light is going to have kinetic energy. We also have the rules that energy has to be conserved at all times in all frames of reference. Once again, we have to place some sort of relativistic adjustment. And if you start with the work-energy theorem and work your way through the ideas, you end up with this equation where the relativistic kinetic energy is going to be gamma minus 1 in parentheses times mc squared. It's a little different than what you were expecting. We're not quite to E equals mc squared, but we're close. In this case, m is the rest mass, which is the mass of the object when it's standing still. That should give you a clue that things are going to get weird. And u is the velocity of the object. Once again, at low velocities, this is exactly the same as classical kinetic energy. But one of the things that it does tell you is that an object that has mass can't get to the speed of light, because it's going to take an infinite amount of work to get that amount of energy, to accelerate it to the speed of light. And with this adjustment, you do get conservation of energy as long as you can wrap your mind around the idea that mass is going to change to energy. So here we have the basic equation for the total energy. And you're going to take the kinetic energy with the relativity adjustment and add in the rest energy if the object is sitting still. So it's a lot like what's the potential energy, what's the kinetic energy, add them together. And in this case, the rest energy is going to be the mass of the object when it's standing still times the speed of light squared. And it comes down to the idea that energy is equivalent to mass. So now you have that final equation you've been waiting for. E equals mc squared with a little bit of an adjustment in it. Bye-bye.